Hi, everyone. I'm Josh. Sorry I can't be there in person. I recently finished my PhD at Princeton. I'm now at AWS. And yeah, I'm going to talk about verified pattern matching compilation and algebraic data type axiomizations. So algebraic data types and pattern matching are extremely useful features, both for writing functional programs as well as for verifying and reasoning about programs. And accordingly, they're found all over the place. They're found in languages like OCaml and Haskell and Scala and so on, in proof assistants like Rock and Lean, as well as even in imperative verification tools. Functional programming is still very useful for specifying and verifying things about imperative programs. So these features are also found in tools like Daphne and Verifast, as well as the kinds of intermediate languages that these SMT-based verifiers are built on, like Y3 and Viper. However, most of these tools do not actually have these features as primitives, and so they need to be compiled. And the exact compilation depends on the setting that we're working in. In OCaml, for example, pattern matches get compiled to decision trees, whereas algebraic data types are ultimately represented as pointers in memory. In Rock, algebraic data types are built into the calculus of inductive constructions, but complex pattern matching is not and needs to be compiled into simple patterns, which we'll talk about in a minute, in the front end. And similarly, in tools like Daphne and Y3, pattern matches need to be compiled to simple patterns. And here, algebraic data types are not built in. We're targeting SMT formulas, and so they need to be axiomatized as first-order formulas. And it's interesting to note that the same sorts of pattern matching compilation algorithms can be used for all of these cases, at least if we ignore dependent pattern matching. The question is, how do we know that all these compilation steps are correct? And especially in verification settings, it's very important that our tools are sound, and algebraic data types and pattern matching are at the core of a lot of these different tools, and they interact in subtle ways with other features of the logic, things like termination checking and positivity checking and exhaustiveness checking and so on. And so getting some of these definitions or compilation steps slightly wrong can make the tool unsound and make it so that the tool is not trustworthy. So in this work, we look in particular at the Y3 implementations of these steps, although we'll see how this can be extended to other settings as well. And we verify the soundness of these key compilation steps in the Rock proof assistant. In particular, we give the first verified general purpose pattern matching compiler, and we have to formulate lots of different properties about exhaustiveness checking, about pattern matching compilation, one of which is exhaustiveness checking. Another is a property that we call robustness that allows us to discover a bug in Y3. And then we use this pattern matching compilation to give a first order axiomatization of algebraic data types, which is the first formally proved sound axiomatization. Just a little bit of background. We're building on some of our prior work on formalizing the semantics of Y3's logic in Rock. And this logic is first order logic with a lot of useful functional programming features like polymorphism, of course, algebraic data types and pattern matching, recursive functions, and inductive predicates. The exact details of this are not important at all for the purpose of this talk. Basically, everything that pretty much everything I'll be talking about, you can think about, say, OCaml pattern matching, and everything should work out very similarly. On that note, what is the actual setting that we're looking at? Well, we have patterns which should hopefully be familiar. We have wildcards, variables, constructor patterns, or patterns, and as patterns, which match the inner pattern and bind the result to the variable. And even this simple notion of pattern matching can get complicated. We can have nested matching, simultaneous matching, and there's deep interaction between pattern matching and termination checking, which is not so relevant for this talk. So our prior work on formalizing Y3 in Rock includes pattern and pattern matching syntax, typing, and semantics, which is helpful because it gives us a way something to prove the algorithm correct against. And what is this problem of compiling pattern matching? So we want to take a pattern match that looks something like this term here on the left, where we have some nested matching, say in the singleton case, as well as simultaneous matching. And we want to transform it into a term that has only simple pattern matches. And what I mean by that is that there's no nested patterns, there's no simultaneous matching. Every single pattern match occurs only on constructors applied to variables or wildcards. And so these are essentially decision trees where we just case on which constructor to go in. And I show an example on the right-hand side of one possible compilation of this, this match. And it turns out that this problem is very related to the question of exhaustiveness checking. And so we'd also like the algorithm to tell us if the match is non-exhaustive. If we forgot a case, then it should correctly tell us this is non-exhaustive. There are lots of different, there's been lots of work in this general area of pattern matching compilation because it's so widely applicable to languages like OCaml and Haskell. I show here just a selection of some of the papers that have been studying algorithms for this purpose. And a few of these papers have some pen and paper proofs that their algorithm is correct. Unfortunately, none of them actually implement or verify these algorithms with formal proofs of correctness, which is what we are focused on today. So we're looking at a particular algorithm due to Marangé, which by this point has become pretty standard. It's very similar to what's used in the OCaml compiler. Of course, it's what Y3 uses. I believe Daphne does something similar. And it's based on an idea of interpreting pattern matches as matrices, and then defining some decompositions of this matrix for the algorithm. So if we take a look at the pattern match we saw in the previous slide, we can interpret it as the matrix that we see here on the slide, where each row of pattern matching becomes the corresponding row in the matrix of the patterns, followed at the end by the result of result of that case. And the first decomposition that we need is called specialization, which is with respect to a given constructor C, and it's intended to give us the remaining pattern match, assuming that the first term that we're looking at matches constructor C. So if we look at our example here, if we know that the first term matches nil, then we have to be in case either 1 or 4, and the remaining match is simply the rest of the terms in the simultaneous match. So we have nil x1 and then cons wild x4 for our matrix. Meanwhile, if we know that the first term matches the constructor cons, we know that we have to be in case either 2 or 3. And here we can't just proceed with the remaining simultaneous matches. We first have to match the inner patterns of the cons. And so our matrix becomes first wildcard nil, followed by the rest of the matrix, and then wild, followed by the rest of the matrix, or the rest of the row. Now, the second decomposition we need is called the default matrix, or D, which gives us, or is intended to give us the rest of the pattern match, assuming that the first term does not match any constructor that appears in the first column. And so if we look at this other example here, if we know that we don't match any of the constructions in the first column, we have to be in case either 2 or 3, and then the default matrix is simply the remainder of each row. And so this gives us the sort of simplified view of what the algorithm looks like, which says that if we're looking at some termless T's, we should nest our terms in some sort of defined order. And in this case, we're just looking at in the direct order of the term, but there's been some work in choosing good orderings and various heuristics for this to minimize the size of the resulting term. And then based on what appears in that column, we take each constructor that appears in the first column, we give it a case in our match instantiated with some fresh variables. And what do we return in that case? We simply return the recursive result of calling this compilation algorithm on these new variables, which match the inner patterns of the constructor, and then the remaining term list with these specialization matrices. And then finally, at the end, if we are missing a constructor, we need this default case. And it's not super important that you necessarily understand exactly how the algorithm works. It takes a little bit of getting used to. There's an example in the paper to kind of work through it in more detail if you're interested. But yeah, this is kind of the basic approach of the algorithm. This so far only works if we have wildcards and constructors, but of course there are other kinds of patterns as well. And so there's a pre-processing step to handle these. If we have variables and bindings, those turn into let bindings in the last column of the matrix. More interestingly, the OR patterns here can get expanded essentially into 2 different patterns. This is going to cause us problems in a little bit. There's an additional optimization that Y3 in particular uses, which is if we're matching on a known constructor, like say the singleton list, we can directly evaluate that match in the corresponding constructor. So we don't actually need to kind of create every single constructor appearing in the column. We only need to focus on the one that we know is going to match. And this is very useful in the case of Y3 because this is how it implements simultaneous matching, where it's actually implemented in the front end as just matching on tuples, and it's quite easy to see that it desugars into the simultaneous match that we expect. And this will also cause some problems for us in a few minutes. So there's a lot of properties of pattern matching compilation that we want to formalize and we want to verify about this algorithm. The first one is termination. So you'll notice that if we look at the example of the algorithm we saw before, the recursion does not occur on any subterms of the original matrix. It occurs on these matrix decompositions. And we might hope that, well, at least the decomposition should be getting smaller in some sense, say like the total size of the matrix. But in fact, that's not the case, thanks to these OR patterns here. When we expand an OR pattern into two different rows, you'll notice that we end up duplicating this pattern P3. And of course, we could have many patterns in a row. We might end up duplicating many things. And it's very easy to construct examples where this matrix just becomes much, much larger when we have these OR patterns. And there's this kind of difficult interplay between times when the matrices are shrinking and times like with these OR patterns that the matrices are growing that we have to reason about. Now, there's another complication that comes from these specialization matrices. So if we take a look at this example here and we try to specialize it using cons, if we know that our first term is matches cons, we can be in either case 2 or 3. And if we're in case 3, well, we need to match the inner patterns. If the overall thing matches a wildcard, the inner patterns also match wildcards. So we simply add 2 wildcards to the resulting matrix. But the problem is this means that in this S matrix, we're actually adding additional wildcards for each argument of the constructor. And if you imagine a matrix where there are many rows that have wildcards in them, you end up adding lots and lots of wildcards to your new matrix. So this is another case where these matrices can get larger throughout the course of the algorithm. So the question is, how can we actually prove that this whole thing terminates? And the intuition is that if we first expanded all of the OR patterns in the whole matrix, and then we ran our algorithm, we could almost convince ourselves that it terminates. We just have to make sure we sort of add enough fuel to overcome all these added wildcards we saw in the previous slide. And so this is basically how we design this termination metric. We take the size of the fully expanded matrix, which is taking recursively all of the OR patterns and expanding them all out. And we have to parameterize it by some additional fuel to overcome these additional wildcards we're adding in the constructor case. And the exact value that we have to add is basically the number of rows of the matrix times the largest number of arguments to any constructor in the matrix. And we can be assured that this is definitely going to be at least as large as the number of wildcards that we'd add. We sort of consider the worst case is we have to add k wildcards at each row. Now, this metric is difficult to work with. This expansion function and this bound change throughout the algorithm as the matrix P is growing and shrinking and changing number of rows and columns and so on. And so we need all sorts of monotonicity results to be able to bound these values appropriately throughout the algorithm. But we can then prove that these specialized and default matrices will decrease under this termination metric. And we can combine this to show that the algorithm terminates. And it's worth noting that this shows not only that this algorithm terminates, but that any similar algorithm that's based on these kinds of matrix decompositions terminates. And there's many variations. There's different orderings you could use. The same termination argument would suffice for all of them. So the second thing we need to reason about is the semantics. Namely, if the compilation of this pattern match succeeds and it gives us some term, then the semantics of matching this matrix against the term list also succeeds, and it gives us something that's semantically equivalent to the compiled term. And I just want to take a brief detour and talk about what this semantics actually entails. So this is from our prior work on formalizing semantics of Y3, and this is a Hilbert style or denotational semantics, which means that Y3 terms and formulas are interpreted as objects in Rock's logic. So for instance, a Y3 and becomes a Rock and so on. And the little complication is that when we might have a term that has some uninterpreted type or function or predicate symbols in it. So to give those a particular meaning, we do this with a given interpretation. And likewise, we might have type and term variables in our term, which we give meaning with a valuation. And the way that these recursive structures, like algebraic data types or recursive functions, are handled is that they impose particular conditions on these interpretations. And so for algebraic data types, what does that look like? Well, the conditions we need are that the interpretations of the constructors are injective, the interpretations of the constructors are disjoint. There's a computable function find that tells us for any instance of the interpretation of algebraic data type, which constructor and arguments give rise to that data type. And then there's a generalized induction principle, which is not actually relevant for our purposes for this talk. And in our prior work, we show that all these conditions are satisfiable if everything is well typed. We can construct the models for them, and so on. Pattern matching, meanwhile, is based on using this find function to basically semantically match the term and see which constructor it's in. And the end result is something that changes the variable valuation and describes the valuations of these newly bound variables in the pattern match. And so it's straightforward to extend that from matching individual patterns to matching rows of patterns and matching matrices and so on. But this means, going back to our compilation, that when we're reasoning semantically, we're reasoning about these interpretations, about these conditions on the algebraic data types, about this find function, and so on, which is quite a bit different than standard reasoning about these kind of matches in the literature, which are based on more syntactic reasoning, where you're matching on values. You say something like a constructor applied to some values matches a constructor applied to some patterns if and only if each value matches the corresponding pattern. And this is different than our setting because here the meaning of a pattern match depends on the interpretation. So for example, if I have some uninterpreted function symbol foo of type list, I don't know semantically if that thing equals nil or cons until I actually give a particular interpretation. But the idea, once we sort of get a handle on all of this, is we can prove the semantics of these S and D matrices, basically prove that they align with the English descriptions that I gave a few minutes ago. We can prove that this pre-processing step preserves the semantics, and then finally combine it to show that the whole pattern match, or the whole compilation algorithm preserves the semantics. And once we have this, this immediately gives us an exhaustiveness check by just taking the contrapositive of our correctness theorem, which says that if the pattern match semantically does not match, there's no row that matches it, then the compilation algorithm will correctly return non-exhaustive. And this allows us to then add to the Y3SEM type system an exhaustiveness check, basically that this compile has to return some, which was not there before. And you might ask, what about the other direction? What about the completeness of exhaustiveness checking rather than just soundness? And there's some existing work in this Marge 2007 paper that proves the other direction in the context of call by value and lazy evaluation. In our setting, interpretations and this kind of reasoning makes this a little bit trickier, where we would be able to prove similar things, but we have to carefully quantify over interpretations in particular places. I might talk about this a little more in the paper if you're interested. But it turns out we didn't actually need any of that. We don't end up proving the other direction. So once we have an exhaustiveness check in the type system, then we have lots of functions that operate over terms, and we'd like to know that they preserve typing, and so in particular that they preserve this exhaustiveness check. And these are functions like substitution and alpha conversion and rewriting and so on. And this requires us to show that this exhaustiveness check continues to succeed in the presence of some reasonable changes to our types and terms and patterns and so on. When we call this property robustness, the problem is that the Y3 implementation does not actually satisfy this property. And the problem comes from this constructor optimization we saw before. So we saw that if we match a singleton list, we can directly evaluate it. We don't actually need all of the different cases. And this is great, except if we take something matching on, say, a singleton list and try to rewrite it into just a variable, and you can run this rewrite in Y3 just like you can in Rock. And the end result is that Y3 crashes with an exception and says that you have something that's ill-typed, your pattern match is not exhaustive. And this is a problem. This prevents us from doing things like lifting common subexpressions into let bindings and so on. And so we found and reported this bug to the Y3 developers. The question is, how can we fix it? So one thing we could do is just to take out this optimization entirely. That's what, say, Rock and OCaml do. They require every case no matter what. But this doesn't work for our purpose. We actually do need it for compilation. We need it to implement these simultaneous matches with tuples. We need it to make sure that the resulting patterns are as simple as possible for SMT solvers. And so our solution is to create two versions of this algorithm. One that does not have this optimization we use for exhaustiveness checking, and the other that we use for compilation. And then we need to prove two things. We need to prove that this new version satisfies a robustness property. And I don't give the precise property here because it's quite complicated, but take a look at the paper if you're interested. And then we have to prove that this new version, this exhaustiveness check, is strictly stronger than the compilation version. And we're going to need this in a few minutes when we're actually doing the elimination of pattern matches, and we want to make sure that we don't hit any exceptions along the way. So once we have all of that, we have a pattern matching compiler that's verified with all these properties, and we want to use it to axiomatize algebraic data types. And so the axiomatization basically consists of three main steps. First, we have to make our particular types and constructors that we're axiomatizing abstract. We have to introduce some new function symbols. We'll see what those are in the next slide, and we give them axioms to define their behavior. And then we have to compile and eliminate all the pattern matching by rewriting using these new function symbols in all of our terms and formulas. And so, okay, what does the axiomatization look like? There's a lot on this slide, so bear with me for a moment. This is an example of Y3's axiomatization for lists. And so we see there's three kinds of function symbols that are added. We have projections, which allow us to extract the arguments of a given constructor. We have selectors, which axiomatize simple pattern matching. And we have indexers, which tell us which instance of an algebraic data type we are in. There's two additional axioms as well. There's a disjointness axiom that tells us that our constructors are distinct, and an inversion axiom that tells us that every instance belongs to one of our constructors. And this is, as I mentioned, the particular axiomatization Y3 uses. There are many slight variations for other tools, but most of them have a pretty similar flavor when you're sort of axiomatizing these types for SMT solvers. But what does the elimination of pattern matching look like? Depending on the particular setting that we're looking at, either it'll use this selector function symbol that we saw on the previous slide, or it will directly encode this pattern match as a particular formula. And it turns out it's very, very important that for this whole method and then for any sort of proofs about it to work, it has to be the case that all these pattern matches have been compiled, that they're all simple, and that, that there's no nesting or anything like that. And this is the case where we need that relationship between our new exhaustless checker and this compilation. We have to know that when we actually compile, we're going to succeed and result in patterns with the right shape that we need. And this follows from the exhaustless checker and the type system. But once we have all this, how can we put this all together to prove soundness? So first, we have to define a new context that has all of these new types and function symbols. Then we need to construct interpretations for the new symbols. And so this is basically giving the semantic meaning or the intended semantic meaning to each of the symbols that we add. And we can sort of validate this by proving that all of the axioms that we're adding are satisfied by this interpretation, which allows us to safely add these axioms. We prove that this pattern matching elimination preserves the semantics where the new term is evaluated in this new interpretation. And it's very important we actually have like equivalent semantics. We can't just prove kind of soundness or one direction, because we do need to reason both in hypotheses and goals. We have to prove that everything is well typed, which turns out to be surprisingly tricky and tedious, but I completely ignore it for the purpose of this talk. But once we put this all together, the result is a first order axiomatization of algebraic data types that is computable in ROC and also has a corresponding proof of soundness. There's been, as we saw, there's a lot of work on pattern matching compilation, but there's very little work on verified compilation before our work. Pretty much every existing tool out there, like CakeML and MetaRock, really are only handling simple patterns. The most relevant work in terms of the algebraic data type axiomatization is a tool called Sniper, which is an extension to SMTCock that turns ROC goals into first order formulas and sends them to SMT solvers. And basically it generates theorem statements and proof scripts that assert that these axioms that you're sending to SMT solvers are in fact true for the particular input you're looking at. So this differs from our approach. This is a certifying approach where it's generating these theorems and proof scripts for particular instances, rather than our approach where we're proving soundness once and for all. And then, of course, there's been lots of work, especially in recent years, about competitors of Y3 and proving things about their semantics, but this does not generally include algebraic data types. So to wrap up, pattern matching compilation is pretty complicated. Despite this, we give the first formally verified sophisticated pattern matching compiler and first order algebraic data type axiomatization, which is a key step in enabling verified and more trustworthy verification tools like these intermediate verification languages. We'll note that many of our results are more broadly applicable. We saw this a little bit with termination. Our pattern matching compiler is quite general, a little more general than it has to be just for Y3, and we could make it even more general, removing some more dependence on Y3. And even though we prove things about the particular first order axiomatization Y3 uses, we talk in the paper about how our methods would also extend to similar or other first order axiomatization, like, for instance, the one that Daphne uses. Thanks everyone for listening, and I will now take questions.
Thanks a lot.